Hey, all you cool cats and kittens. If you didn't understand why I just said that, you haven't been watching Netflix enough. Just kidding. Anyway, Mr. Retan here, here to help you with your pre-calc assignment this week. So first thing you have to do for your pre-calc assignment is answer this question that we talked about in my family a few nights ago. And then you're going to go on and work on some math. So our focus this week is on trig identities. And so part one involves an introduction. And so if we were in class, I'd say, please get up and pick up the notes handout. And then I would talk through the notes with you and explain them in detail. And that's what I'm going to do in this video. So what you're going to need to do is click on the open the notes document right here. So when you click on that and you open that up, then once you open that up, you can start going through each of those parts of the notes. So I'm going to explain those right now. So the first thing the notes talk about, one second. So first thing the notes talk about is just really what an identity is. So there's some definitions that we need to make sure that we understand. So it says an equality is a statement that is, so we're going to say always true. So an example of an inequality or an equality would be something like 3 equals 2 plus 1. It's always true. There's no arguing about that. Or a half plus a half has to equal 1. It's always true. That's an example of an equality. An equation is something that is conditionally true. And what that means when we say conditionally true, we're talking about something that might be true depending on the variable. So 2x plus 1 equals 11. So if I say x equals 3, it's not true. It's false. But if I say x equals 5, then it would be true. So it just depends on what your x value is. And then the last one, and this is the one we're going to focus on, is called an identity. So an identity is a statement that is true, we're going to say always true for all numbers in the domain. Now, I'm going to say a little bit more about that idea of the domain here. So depending on the problem, some numbers might work and some might not within an identity. So I should have been a little clear maybe at the beginning. You should be following along in the notes handout, and you can either write these notes on another sheet, or if you have access to a printer, print the notes and then just fill them in like we would in class. So the next thing it mentions in your notes is this idea about what if I had an expression like this, x over x equals 1. So this is an example of an identity. It's an algebraic identity. So x over x equals 1 is true for just about any x you can think of. So 3 over 3 is equal to 1, or 8 over 8 is equal to 1. But there is one x that would cause trouble. If I did 0 over 0, that's not going to be equal to 1. And that is an example of what we call the domain of validity. So down below there, it mentions this idea of the domain of validity. And this is just a fancy name for the numbers that you can plug into an identity that makes sense in that problem. So that's an important idea for us as we think about this. All right, so we're going to continue with some examples. I want to give you, actually, before we go on, I'm going to give you a couple more examples of identities. I forgot about that. So another example of an identity would be like A plus A equals 2A. Any A that I plug in, it's going to work. 3 plus 3 is 2 times 3. Another example would be something like, I'll write it down here so where we have more room. Here's another example. If I had A plus B times A minus B, that should always equal A squared minus B squared for A and B. So these are all examples of algebraic identities. But what we're going to focus on are something called trig identities. And trig identities are identities that involve trig expressions. So in your notes, that's the next thing. So one more time, trig identities are identities that involve trig expressions. So we're going to work through some examples. Give me a second here. All right, so statements like tan of theta is equal to sine of theta over cosine of theta, or secant of theta is 1 over cosine of theta. These are examples of some basic trig identities. So we're going to work through, first we're going to write some of these identities down. So where it says basic trig identities, first want you to write down what are called the reciprocal identities. So let me clear my whiteboard a second. All right, so there we go. So first thing we're going to do where it says basic trig identities, I'm going to have you write down some of these what are called reciprocal identities. So sine of x is the same as 1 over cosecant of x. That's the first one. Another one, if we think about cosine of x, we know that that's the reciprocal of secant of x. Okay, and then this last one is if I have tan of x, that's the reciprocal of cotan of x. So 1 over cotan of x is the same as tan of x. Along with those, we could say that cosecant of x is the same as 1 over sine of x. We could say that secant of x is equivalent to 1 over cosine of x. And we could also say that cotan of x is equivalent to 1 over tan of x. So these are called the reciprocal identities, and these are probably the most basic identities. They should look somewhat familiar to you. You've seen this idea already. And then the next one, these are called the quotient identities. So the quotient identities are the ones that say if I have tan of x, it's going to be equivalent to sine of x over cosine of x. And that makes sense because we know that sine over cosine is like saying y over x, which if we think about tangent is change in y over change in x, or slope on the unit circle. If we flip this around and think about cotan of x is the same as cosine of x over sine of x. So we're just flipping that first fraction because it's cotan, which is reciprocal. So these are some of the very basic identities. Now, trig identities can be used for two main purposes in math. One of them is to simplify expressions. The second reason we use these is to try to verify if expressions are equal. So because of our limited time and being just virtual this year, we're going to focus on the idea of simplifying. So we're not going to worry about the verifying part. Just I'm going to have you work on some problems dealing with simplifying. All right. So if we continue on in our notes, we have some specific examples. So example number 1, if I have cosecant of theta. Now the other thing I forgot to mention is the x and the theta really don't matter. It just depends on what variable you're given. I wrote all those identities using x, but we could have theta as well. All right, so the first one, example number 1, let me walk through that with you a second. All right, so if I have cosecant of theta times sine of theta. And I want to simplify that. What I'm going to do, let me make my screen bigger for you. What we're going to do is change everything into something involving sines and cosines. And this is a strategy you're going to use again and again in this section. So we're always going to think about how could I change this into something involving sines and cosines. All right, so cosecant is the same as 1 over sine of theta. And we're going to just keep sine of theta the way it is, sine of theta. And the reason we're doing that is because now I can cancel or simplify this expression. So I have a sine on the top and a sine on the bottom. So I'm going to cross those off, and I'm left with a 1 in the top of the fraction and a 1 in the bottom. Remember, we go top times top, bottom times bottom. 1 over 1 is the same as 1. So that first expression is the same as 1, simplifies to 1. All right. If we go on to example number 2, in example 2, we have cotan of theta times tan of theta. This again is pretty basic. We're starting very simple. This one also illustrates something about identities that's important for you to understand. There's a lot of different methods in order to simplify an identity. Usually there are simpler methods than others. And you'll kind of start to feel about which one is simpler as you do more of these. But in this one, I'm going to show you 2 different methods. So one method I could do, I'm going to change cotan to 1 over tan of theta. And I'm going to keep tan as it is. And you can see that the tans are just going to cancel, and I'd be left with 1. Okay, so that would be like method number 1. Method number 2, and this is the sine cosine strategy. When in doubt, always change things to sines and cosines. Every trig expression can be written using sines and cosines. And it's important to remember that as we work through these. So cotan of theta is the same as cosine of theta over sine of theta. And tan of theta is the same as sine of theta over cosine of theta. And so those are going to cancel. The cosines cancel, the sines cancel, and again, we'd be left with 1. You might think, well, why would I do it that way? This way seems simpler. True, in this one, probably this way is simpler, but in general, if you're stuck, you can always change things to sines and cosines, and that's always a good strategy. All right, so if you look on in your note handout, there are 3 problems below that say try these. So if we were in class, I would give you 5 or 10 minutes to try these, and then we would put them up on the board. So I want you to pause the video and try these on your own. And then in a minute, I'm gonna walk through those. So pause it, work through them, and then watch the rest of this video to see how those are done. All right, so hopefully you've paused the video and you've taken some time to try these on your own. If you haven't, do that right now, because I'm going to start going through those 3 problems with you. And I think there's more value in you trying them first before you just watch me do it. So here we go. These are, again, pretty basic starter examples of identities, but I think it's a good idea to start basic. So we have cosine of theta times tan of theta. So if I want to simplify that one, I'm going to keep the cosine as a cosine because I know that I can rewrite tan as something involving sines and cosines. So I know tan is the same as sine of theta over cosine of theta. Now, one thing I've noticed with students is they start changing things just to change them. So we want to be kind of strategic here. For example, if I change tan to 1 over cotan of theta, that's really not going to help things because I don't have cotan here, but I do have a cosine here, and that's why this idea of sines and cosines is useful. So you don't want to just blindly change things to something else. You want to be strategic about it. All right, so then remember, when I see cosine, that's a fraction. And so then I can see that, oh, cosines are going to cancel. And I'm left with sine of theta in the top. So sine of theta over 1. And then sine of theta over 1 is the same as sine of theta. So that's how you simplify the first one. That second problem, we have secant of theta times cotan of theta. So again, when in doubt, sines and cosines. So I'm going to change secant to 1 over cosine of theta. And I'm going to change cotan of theta to cosine of theta over sine of theta. So I'm trying to be strategic, all sines and cosines. Then I'm going to cross off the cosines. So I cross off the two cosines and I'm left with top times top, bottom times bottom. So 1 over sine of theta. So 1 over sine of theta is the same as cosecant of theta. And that's as simple as we're going to get that one. So the third example, we have tan of theta squared times secant of theta. One thing for you to keep in mind, when we have powers with trig expressions, those powers usually are written like this. So usually you would see it like tan squared theta, secant theta. And the reason we usually write it this way is because if I wrote it this way, that parenthesis, if it's left out, somebody might think it's just the theta squared, which is something different. So you want to make sure that in general, you realize that power usually is right there. Now, a lot of times it's easier to rewrite it as the one up here. This is really what that means. But you want to be mindful of that as you do these problems. All right, so tan of theta squared, I'm going to think of this as sine of theta over cosine of theta times sine of theta over cosine of theta, because that was the tan times the tan. And then I've got to shift my camera here so you can see what I'm doing. All right, and then I have secant of theta. So secant theta is 1 over cosine of theta. So now when I look at this, I need to pause the video to figure out what the heck to do with this problem. 1 second. Okay, I realized I had the wrong copy up of your notes, and so question 3, I was changed. Everything else should look the same as what you already looked at and what we talked about. So question 3 really should say sine theta squared times secant of theta. So we're going to revise that right now. So let's go back to that problem number 3, and we're going to rework through that. All right. So so I ran into an issue here. So I'm going to get rid of this. So hopefully this doesn't confuse you too much. Question 3 really should be sine of theta squared times secant or cosecant. I think cosecant. 1 second. Secant. Okay, times secant of theta. So secant of theta. So same idea as what we had before with tan and the powers, like I was saying, but it should be sine of theta times sine of theta, and then we have secant theta is 1 over cosine of theta. And so the way we're going to deal with that is we are going to combine these two. I'm going to think of this as over 1. And again, you could think of this as over 1 also, but we really don't need to, because if I look at this, this is going to be the same as sine of theta multiplied by sine of theta over cosine of theta. And sine of theta over cosine of theta is the same as tan of theta. So this is the same as sine of theta times tan of theta. And that would be your final result for that one. Now, when you look at that, you might think, well, that's not much simpler than what we started with up here. And I agree, it's not much simpler. The big difference is this one has a power, it has the squared. This one doesn't. So that's why it's considered simpler. So hopefully those examples help. So what you're going to do next is I provided you a list of basic trig identities. So if you go back to your assignment, which we'll do right now, 1 second. So within your assignment, when you go next to the note sheet, there's a list of important trig identities. So if you click on that, that list of identities has several identities that we are going to use. When you go through, what I would recommend is you make your own list or print out this list and fill them all in. So the first couple categories we've just filled in already, and I'm going to walk you through filling in the rest of those in a minute. All right, so that list we've already talked about the reciprocal and the quotient identities, and so I'm gonna shift down to the Pythagorean identities, and like I said, you should be filling these in as we talk through them. All right, so the Pythagorean identities are based on the Pythagorean theorem, and so if we think about the amazing unit circle, let me expand this. The amazing unit circle, if I have a right triangle, and I'm just going to draw it in the first quadrant just to help you think about it in a simple way. We know that the x is the cosine of an angle, so we know this is cosine of theta. The y is the sine of that angle, so sine of theta is your y coordinate. So this side of the triangle is cosine of theta, and this side of the triangle right here is sine of theta. And we also know, because this is a unit circle, we know that the radius of this circle is 1. So a right triangle, that Pythagorean theorem says that cosine of theta squared plus sine of theta squared has to equal 1 squared. Now, we don't usually write it that way. Just like I was mentioning before with the powers, we put the powers on the inside. So, and usually we put sine first. So sine squared theta plus cosine squared theta always is going to be 1. And that's the first Pythagorean identity. So under that category where it says Pythagorean identities, so the first Pythagorean identity, and this is probably the most important of them, is that sine squared theta plus cosine squared theta is always going to equal 1. Now I'm using theta here, but once again, we could use x or any other letter that we want, as long as we're consistent. So whatever letter they give you in the problem, just stick with that letter. Theta puts the focus more on the idea that it's an angle versus just a variable. We can also derive a couple others from this one. If I move the cosine over, I can see that, oh, that means that sine squared of theta is 1 minus cosine squared of theta. I can also see that cosine squared of theta, if I move sine squared over, is 1 minus sine squared of theta. Those are just based on some algebra, shifting this first one, shifting one term to the other side. Okay. Beyond that, there are a couple other ones that go with this. One of them is that 1 plus tan squared of theta, 1 plus tan squared is the same as secant squared of theta. Okay. And then the last one is that 1 plus cotan squared of theta is the same as cosecant squared of theta. So those are all the Pythagorean identities. Now below that, we have a few other categories, and I'm going to walk through those with you right now. All right. So the cofunction identities say that if I have something like sine of x, it's the same as cosine of pi over 2 minus x. Now, remember in radians, pi over 2 is just 90 degrees, which is in degrees. So you could write this as 90 minus x also if you were in degrees. Let me explain that one a minute with you and why it makes sense. So again, on the unit circle, if I took the sine of 30 degrees and then I took the cosine of 60 degrees, and we think about those as x and y coordinates on that unit circle, at 30 degrees and at 60 degrees, if you compare those x, y coordinates, we know that they just flip-flop. And so it makes sense that the sine and the cosine of those just flip-flop. And so we kind of have this dividing line at 45 degrees. And so if we go beyond that, the x and y are the same right here, and they're flip-flopped, kind of reflected over that xy as you go out. And so that's what this is getting at. So in turn, we could say cosine of x is the same as sine of pi over 2 minus x. We can do the same with all these other different functions. So we could say tan is the same as cotan of pi over 2 minus x. We could say that cosecant is the same as secant of pi over 2 minus x. And secant is cosecant of pi over 2 minus x. And cotan is the same as tan of pi over 2 minus x. Now, as you watch this, if you miss any of these any of these identities, if you're trying to write them down, there's also a link below a little lower in the assignment where it has all the identities. If you Google Trig Identities list, you're going to find all of these. Or if you wanted to just Google cofunction, I'm sure you would find some other explanations about why this makes sense. And so it's kind of up to you of how well you want to understand this. You just have to seek it out. Even odd. So when we think about sine and cosine, first of all, the sine wave looks something like this, the basic sine wave. So sine is an odd function. So that means, if we recall from earlier this year, opposite x's give you opposite y's. So, so opposite x's, opposite inputs, give me opposite outputs. So I'm going to say sine of negative x is the same as negative sine of x. The negative can come out front. Okay. With cosine, cosine looks a little bit different. So cosine is a wave also, but cosine starts up here, sort of like that. Now cosine is an even function, which means it's symmetrical about this y-axis. So opposite inputs give me the same outputs. So it doesn't really matter that I have that negative there. So cosine of negative x is the same as cosine of x. Tangent is a combination of the two. Remember, that's sine over cosine, so the negative is going to stay there from this one. So this is negative tan of x. Okay? And then if we go on to these other functions, they're reciprocals, and they're going to have exact same properties. So sine and cosecant, reciprocals, it's just going to maintain that negative on the outside. So it's still an odd function. So negative cosecant of x. Secant of negative x is negative, secant of negative x is negative secant of x. Or actually, I'm sorry, the negative's not going to be there with that one because it's the reciprocal of cosine. And that last one, cotan of negative x, is the same as negative cotan of x. So those are the only identities that we're going to use right now and that I'm going to have you focus on. If you continue on this sheet, you'll see a bunch of other categories. And if you Google lists of identities, you're going to see things like half angle, double angle, and angle sum, angle subtraction, those kinds of identities. Because of the situation we're in learning at home, we're going to try to keep it as simple as possible and just stick with these identities. So what you're going to do in your assignment this week is you're going to work through the problems. I believe there's 6 problems that you're going to do, and there's an answer bank on the bottom. Once you finish those, you're going to check those answers using the key that I provided. And then you're going to go on and watch another video with a few more complicated examples. And you're going to try a few more problems, 6 more problems. You're going to take pictures of the work that you do this week, and you're going to insert that into the Google Doc, and then just turn that in when you're done. So remember, I'm looking for you to try these problems. The first set of problems, I gave you the key so you can work on fixing your answers and your steps if needed. Steps are the most important part. But I'm just looking for some genuine effort on your part, just trying these problems. I know it's going to be challenging, so I provided some other suggestions for help at the bottom of the document. So also feel free to send me a message with questions, or I would be glad to meet with you on Google, the Google Meet, if needed. The other thing I was going to remind everyone of is we have a weekly Google Meet. I messed up the time a little bit last week. It's going to be 2 to 3 every Tuesday. So hopefully I'll see more of you all at once from 2 to 3 this Tuesday. So hope everyone's doing well. I miss all of you. Take care. Thanks.